So now here we're going to do this example again. This is a continuation of our previous example in the sense that we're using the same region. Okay. So again, we're going to consider the region y equals 2 cosine of x, y equals we're going to consider the region bounded by y equals 2 cosine x, y equals 0, x equals pi over 6, x equals pi over 2, and our question is, what is the volume of the solid if we rotate this about the x-axis? So now we're going to rotate it like this. Okay. So I always recommend, and again, I know I've mentioned it before 100 times, but I always recommend for you to draw a figure before you do the calculation, because the figure helps give you insight into the technique that you're going to use to calculate the volume. Look what happens here. You might think from the previous two examples that we're going to use the cylindrical shells. But if you notice here, I know this length for every x value. What is that length? Well, it's y equals 2 cosine x. And so it appears that I can calculate this using the disk method with this function representing the radius of the axis of rotation. Remember that if I have a function like this, look, let me draw this. If I have some f like this, let's say, like this, okay, from, let's say, a to b, let's say this is f of x, right? And I want to find the volume of the figure if I rotate it about the x-axis, right? Then what happens is that what I'm doing is I'm making a figure with a cross section, which is a circle that has radius f of x at that particular x value, okay? And so we remember that in general, the volume will be the integral from a to b of our area function, at where area is given at each x value within the interval ab with respect to x. And again, because in this case, when we're doing the volume of revolution here, and the f of x serves as our radius, and because we know that the area of a circle is pi r squared, we can rewrite this as the integral from a to b of pi times, what's our radius? F of x, close parentheses, squared dx. And of course, this is our classic disk method or washer method. We call it the washer method when we're going to subtract out like some interior hollow given by some g of x, let's say. But for us, this is the disk method, okay? And we can see that it's just a natural consequence of our original idea of integrating an area function that gives you the area at each slice, okay? In this case, we can see that we're going to use exactly that, right? So our volume is going to be given by the integral, in this case from pi over 6 to pi over 2 of pi times, right? Pi times f of x squared. And again, remember, f of x has to be the radius of the figure of rotation, right? In this case, it's nothing but the y equals 2x, as we were discussing when we were looking at the figure, right? So it'll be open parentheses 2 cosine of x squared, and then all of that with respect to x, okay? And so now, first of all, I look at this 2 cosine x squared. What is that? Okay. Well, I can see that this will be the same thing as 2 squared times the cosine squared of x. Okay. How do I know that? I know that because I know that the exponential rule, let's say x times y raised to the nth power, is given by x to the n, y to the n. So oops. And so here I applied the 2 to each of the constituent members here. You might say, well, David, shouldn't this be open parentheses cosine x close parentheses to the nth power? Okay. And I want you to remember that in this case, there's a shorthand for this, and it's like this. I know some of you might know this already, but in case you don't, it's a shorthand. So what you saw here when I wrote the cosine squared of x, you can see it exactly as cosine of x in parentheses raised to the, in this case, second power. What does this become? This becomes 2 squared is 4. So this is 4 cosine squared x. So that will allow me to rewrite this integral as the integral from pi over 6 to pi over 2. I can pull my pi out already. And this becomes 4 cosine squared x dx. Okay. Now let me erase all this before we confuse it. Okay. And by the way, I recommend that whenever you're doing like these kind of problems, I want you to think through how you can justify each step just the way that I do, so you can be 100% confident of handling a problem that you may not have seen before. In this case, I'm going to pull out the 4. So that's going to render my integral to look like this. 4 pi integral pi over 6 to pi over 2 cosine squared of x dx. Okay. So now we have to calculate this integral, which I'm going to perform by magic right now. So we have to do this integral. The integral of cosine squared x with respect to x from pi over 6 to pi over 2. Okay. So how are we going to do this? So, and let me just make a brief note. I know probably all of you already know this, but I just want to make sure you guys know this just for sure. Whenever you see something like cosine squared x, what this really means is cosine of x squared. Okay. This is just an accepted shorthand for this. Okay. Okay. So when you look at this, you know, you think to yourself, do I know any function whose derivative is the cosine squared? Whose derivative is the cosine squared of x? And offhand, it's not that easy to see this. Okay. But this is one of the simplest types of trigonometric integrals for which we're going to use this very helpful identity. Let me write that identity for you. We can rewrite the cosine squared of x as 1 plus the cosine of 2x divided by 2. And even though we're not going to use it here, I want to write down for you the corresponding identity for the sine of x. The sine squared of x will be 1 minus cosine of 2x divided by 2. Okay? So now, you could ask ourselves, we could ask ourselves, do we know something whose derivative is cosine? And we do. It'll be the sine. Now, of course, it's not going to be that straightforward. There's going to be a little bit of fiddling that we're going to need to do. Okay? But this identity is going to enable us to integrate the cosine squared of x. Okay? Okay, let's do that here together. So I can write this as, the integral from pi over 6 to pi over 2 of what? Of 1 plus cosine of 2x over 2 dx. Okay. You will see that if I want to, I can pull the 2 out. Now the 2 is in the bottom, so what that actually means is I'm going to pull out a 1/2. Okay. So I can rewrite this as 1/2 integral from pi over 6 to pi over 2 of what? 1 plus cosine of 2x dx. Okay. 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 So now we can break up this integral into 2 pieces. Okay. I can leave the 1/2 on the outside, of course. I can open up a bracket. So this will be the integral of 1 dx from pi over 6 to pi over 2 plus the integral of the cosine of 2x dx from pi over 6 to pi over 2. Okay? Okay. Notice here, what I did from here to here is I applied the rule that if I had that the integral of the sum of two functions like this, f plus g, is going to equal to the integral of f plus the integral of g. Okay? Okay. Okay. You guys with me? Now, this integral is actually very straightforward. Okay? This integral is going to be a little bit, it's not hard, but it's a little more involved. Okay? So I'm going to set this one up for us. Okay? Because I know the following fact. I could ask myself, do I know any function whose derivative is the cosine of 2x? Now, you might think, well, maybe the sine of 2x. But by the chain rule, a 2 would come out, right? So we would have to correct for that. Now, if you can see that, then you already know what the correction is, and you can easily get the antiderivative of this, right? But I'm going to use this as an opportunity to see this as a substitution to help us develop the systematic technique for this, and so that you see substitution in a case where it's relatively straightforward as well. Just to reiterate how you can use substitution. Now you might say, but David, whenever I'm doing a substitution integral, I have some function that contains another function, and that function that's contained in that function has the derivative somewhere on the outside, right? So do I have that here? And in fact, we do. If I look at this as the cosine of 2x, which is what it is, of course, then if I look at 2x as the function that's inside, and in fact, you can see that 2x is the argument of the cosine x in this integral. What's the derivative of 2x? It's 2. Now, 2 is not outside of the cosine over here, okay? But 2 is just a constant. And so whenever you get a constant multiple of what that derivative is, you can always fix it by multiplying by an appropriate constant. Okay, what do I mean by that? Let me demonstrate with this piece of the integral. Okay, so as I claimed, I'm going to let u equal to 2x. Okay, then my du is equal to 2 dx. Okay, and then, and again, just to reiterate, I don't wanna like go off way on a tangent here, but I want you to remember, what is the du? It's always the du dx, okay? Where, of course, this is the derivative of the function u with respect to x. Here you can see that the derivative, that u is 2x, so its derivative is, of course, just 2. Okay. So now, I don't have a 2 dx here, right? I just have a dx. So if I multiply both of these by 1/2, I get 1/2 du is equal to dx, like this. Aha, now we're in business, you see. I can now replace, so far, where I am is I can say cosine of u times 1/2 du, right? What about my limits of integration? Well, my u of pi over 6 will be 2 times pi over 6, which will in fact be pi over 3. Okay? And my u of pi over 2 will be 2 times pi over 2, which will be pi. Okay? So now I can write this as 1/2 open bracket. Now what's the integral of 1 with respect to x? It's just x. So I can evaluate this. This will be x evaluated from pi over 6 all the way to pi over 2. Okay? What about this one? So this one, I'm going to use our setup over here to rewrite it. It's going to be plus the integral. Instead of pi over 6, it's going to be pi over 3. Instead of pi over 2, it's going to be pi. Cosine of 2x, cosine of u. And instead of dx, what's dx? 1/2 du. Okay? And now I close my bracket here like this. Okay? Okay. So now I can bring this down like this. This is going to be 1/2 times open bracket. What is this first part? Well, I'm going to open up a parenthesis. It'll be pi over 2 minus pi over 6. Right? Because remember, this is the antiderivative of the 1 with respect to x. And so I evaluated at the top. What does that give me? Well, it's just pi over 2. Okay? And then minus. And then I evaluate the x at pi over 6 at the lower limit of integration. Well, what's x if you plug in pi over 6? It's just pi over 6. So that's how I got that part. Now I'm going to bring down my plus here. Okay? The 1/2, we remember it's just a constant. So I can pull it out of the integral. So 1/2 integral pi over 3 to pi of the cosine of u du. Okay? Close bracket. Okay. So now we have to do this integral. So I'm going to move this out of the way so we can have enough room to do it. By the way, I apologize if I'm doing like all the breakdown, but you know, I want to make sure that none of you misses an idea here. So now here you can see, well, okay, let me write this down here. 1/2, open bracket, open parentheses. What I want you to see in this first half is that I can put both of these with 6 as the denominator. In particular, by multiplying the top and bottom of this first one by 3. So I'll get 3 pi over 6, right? So I get 3 pi over 6 minus pi over 6. And now what? Plus 1/2. Okay? 1/2. What's the integral of the cosine? The sine. Okay? Right? The integral of the cosine of u is the sine of u. Why? Because the derivative of the sine of u is the cosine of u. Okay. And now we're going to evaluate that from pi over 3 all the way to pi. And then I'm going to close my bracket here. Okay. So now we're going to move on to the next line, so to speak. This part, 3 pi over 6 minus pi over 6 gives me 2 pi over 6, right? So I'm going to have 1/2, open bracket, 2 pi over 6 plus 1/2 times what? The sine of pi, because I evaluated the sine at the top, then minus the sine of pi over 3, like this, and then I close my bracket. You can see that 2 pi over 6 will become pi over 3, right? So this is 1/2, open bracket, pi over 3 plus 1/2 of what sine of pi? Well, if I look at my magical unit circle, okay, if I look at pi, right, the sine is the y-coordinate of the point on the unit circle, right? So it'll be 0. So I know that this first part is 0. Then minus, okay. What's the sine of pi over 3? I look at pi over 3. What's the sine? Square root of 3 over 2. Like this. Okay. Now you can see here, this will be 1/2, open bracket, pi over 3. Then here I have 1/2 times 0, that's 0. 1/2 times negative square root of 3 over 2 is square root of 3 over 4. And then it's a plus, and that's a minus. So it'll become minus square root of 3 over 4. Okay. Or let's put a bracket here. And now finally, if I want to, and I do want to, by the way, I can put both of these over 12 so that I can compress it down into one term. So I could get this, I could get both of these, I can get both of these fractions to have common denominator 12 by multiplying the first one by 4 over 4 and the second one by 3 over 3. So I'm going to get 4 pi over 12 minus 3 square root of 3 over 12. And then finally here, I can throw in the 2, and I can write it in one term as 4 pi minus 3 square root of 3 over 24. Now here I combine them into one term, because once I have them with the same denominator, I can just add or subtract the numerator and keep the denominator. And then I just multiply the denominator by 2, and I got 4 pi minus 3 square root of 3 over 24. And so now we have it. This integral is this. 4 pi minus 3 square root of 3 over 24. Yes. And we see that we get the answer. 4 times pi, open bracket, of 4 pi minus 3 square root of 3 over 24. Okay? Like this. Again, I could distribute the 4 pi into the whole thing. I would get 16 pi squared minus 12 pi square root of 3 over 24. But in this case, I'm going to cancel out the factor of pi, the factor of 4 on the bottom, and I'm going to leave the pi on the outside. Okay? But again, because of the complexity of these answer forms, it may be representable in different ways, and I want you to be aware of it. So you could write it like this. I feel comfortable writing it like this. Or you could also write it like 4 pi squared minus 3 pi square root of 3 over 6. Now, by the way, because I'm saying that I like this one better than that one does not mean this one is more correct than that one, or vice versa. Okay, I just think this one looks a little bit cleaner and more legible. And so there you have it. The volume of the region described here is 4 pi, well, it's pi times, open parentheses, 4 pi minus 3 square root of 3 over 6. Okay? Ta-da!